getting ready to do lesson 6.4 part 2 of pre-calculus math today, classwork. And today we got 18 points here for notebook taking. So have your notebook out, students, or notebook taking guide. And then we got 40 points here in our classwork. So you're going to have to take a lot of notes in this lesson and get ready for that. And our bell work today, students, teachers, is describe how the graph of G is related to the graph of F. So describe how G of X is related to F of X. Same thing down here. Okay. And teachers give your students about 3 or 4 or 5 minutes to respond in your response boxes here. Okay, welcome back for today's solutions, for today's bell work. For 93 here, G of X equals F of X plus 6 is a vertical shift of F 6 units upwards, so this goes up 6 units. And then this here, F of 2X, is a horizontal shrink of F, so the F will be a steeper slope basically. This will be a steeper slope than G of X equals F of X would be a kind of like an identity graph. This will be a steeper than that. It'll be twice as steep as G of X equals F of X. Okay, into today's lesson. First page is notebooks. Students, have your notebooks out or your notebook guides. Finding vector components. You have already seen applications in which two vectors are added to produce a resultant vector. Many applications in physics and engineering pose the reverse problem, decomposing a given vector into the sum of two vector components. Consider a boat on an inclined ramp here as shown. So this would be an application of vector components here. So here's our boat ramp, here's our water, your wheels are down in the water, and then this triangle here is a representation of the boat, the ramp, the axle here, and then the forces here. We'll get into that. Force F due to gravity pulls the boat down the ramp. So here's your force F here, which analogizes the ramp, the steepness of the ramp here, the slope of the ramp against the ramp. So these two orthogonal forces, W1 and W2, W1 is right here, which is this one here, and then W2, which is a force downward and a force down down the ramp, as well as just downward, are vector components of F. So W1 and W2 are called vector components of F. That is, F equals W1 plus W2. So F here, the general force of down of F equals W1 plus W2, vector components of F. The negative component of W1, the negative component of W1 represents the force needed to keep the boat from rolling down the ramp. So the negative of W1 here, in other words, the opposite of negative of W1, would keep it from rolling down the ramp, and W2 represents the force that the tires must withstand against the ramp. So the negative forces of W1 and W2 would resist the boat from going down further into the water on the trailer. A procedure for finding W1 and W2 is shown below. And we'll get into the definition of vector components. So we kind of describe vector components here, W1 and W2. So let U and V be non-zero vectors such that U would equal W1 plus W2. U and V are non-zero here. So U will be W1 plus W2. where W1 and W2 are orthogonal, and W1 is parallel to or a scalar multiple of V as shown. So this is our W2 here, here is our U, and then here is our V here, and then this would be W1 here, and W2 would be here. So where W1 and W2 are orthogonal, meaning that they both kind of work together to go into the general direction of U, is what that means. And over here, let's see, we got W1, W2, again, that would be what would go into the general direction here. Let's see, what direction are the arrows? The arrows are up, so they'd be going up U here. Okay, so that's what we're doing here. Vectors W1 and W2 are called vector components and of U. So W1 here, and W2 are called vector components of U. So this force this way and this force this way are components of the general force here of U, and then same thing over here. W1 is a component of, and W2 is a component of the force of U. The vector W1 is the projection of U onto V. So vector 1 here is a force of U onto V. If V is going this way, then U, or rather W1, will be going the opposite direction here. And it's denoted by W1 equal to the projection of V onto U. So we're projecting V here onto U, is how that would be represented. W1 would be equal to the projection of V U. Projection of V U here. So U, this force U would be, as W1 is concerned, will be the projection of V onto U. The vector W2 is given by W2. W2 here would be U minus W1. So W2 here would be U minus W1. So that would be that force here, and the same thing over here. W2 would equal U minus the force of W1. Okay, so what do we do with that? From the definition of vector components, you can see that it is easy to find the component W2 once you have found the projection of U onto V. To find the projection, you can use the dot product as follows. U would equal W1 plus W2, and then U would equal CV plus W2. W1 is a scalar multiple of V. So W1 here would be what's called a scalar multiple of V. This goes in your notebook. And then U times V would equal CV plus W2 times V. So take the dot product of each side with V. So we're going to take the dot product here on both sides with V. And then we get U times V would be CV times V plus W2 times V. So we're going to distribute our multiplication into our parentheses here. Okay, so moving on now. U times V would equal the magnitude of V squared multiplied by C plus 0. W2 and V are orthogonal. We can do this because W2 and V are orthogonal. So C, when we solve for C now, isolate C, we move this over here, we get C equals U times V over the magnitude of V squared. And W1 would equal the projection of VU, which equals C times V equals U times V over the magnitude of V squared times V. So this becomes a project when we multiply both sides by v in this situation. Projection of vu also equals CV equals u times v over magnitude of v squared multiplied by v. So the projection of u onto v, let u and v be non-zero vectors. The projection of u onto v is given by projection of u onto v would be u times v over the magnitude of v squared multiplied by v. So that would be, this is, in a way, we've done a little proof here by showing this. We've kind of walked through the machinations of arriving here. So decomposing a vector into components. Find the projection of u equals 3, negative 5 onto v equals 6, 2. So then write u as the sum of two orthogonal vectors, one of which is the projection of u onto v. So the projection of u onto v is right here. W1 equals the projection. W1, by the way, is right here. This would be our W1 up here. W1 equals the projection of u onto v. Projection of u onto v equals u times v over magnitude v squared multiplied by v, and then we plug in our values here. So we have u times v over the projection of v squared. So in this case here, when we take our v squared value here and we take the magnitude of v, we come up with 40. And then our 8 here is u times v. So u times v in this case, see, 6, 2, and then u times v, or u 3 times 6 would be 18, minus 10 would be 8, so that's how we get our u times v up here. And then we go through our math here where we multiply our two vectors together, then take the square root, and we come up with 40 doing that. And then we multiply that by our v vector here, which is 6, 2. And then we come out with this. We come out with 6, 5, 6, 5, and 2, 5 for the vector when you multiply this out, as shown. The other component is W2 is, and then when we crank this through, we come out with 9 over 5, and then negative 27 over 5 for W2. So we have our W1, and then we have our W2 here, which is a perpendicular to W1. So there's that diagram again. So u equals W1 plus W2, remember? So when we add our W1 plus W2, we get 3 and negative 5. When we combine these together, we will get 3 and then negative 5. So let's try one now. So we found the components of this. Find the projection of u onto v. Then write u as the sum of two orthogonal vectors, one of which is a projection of u onto v. So here's our u and v here, 3, 4, 8, 2. So W1 would be the projection of u onto v, would be u times v over the magnitude of v squared times v. So when we plug in our values here of u and v, and then we find our magnitude, which is 68, we have 32v, and then v in this situation here would be 8 and 2. We multiply that out, and we get 16 over 17 multiplied by 4, 1 for that. And then our W2, when we crank this through, we find our values here. We have 13 over 17 multiplied by negative 1 and 4. And then when we add these two together, we get that. Okay, so finding a force. A 200-pound cart sits on a ramp inclined at 30 degrees as shown. What force is required? What force is required to keep the cart from rolling down the ramp? So we need a negative force here, W1. Because the force due to gravity is vertical and downward, so it is vertical and downward here, you can represent the gravitational force by the vector of F equals the negative of 200J, force due to gravity. So we need the negative force of gravity. To find the force required to keep the cart from rolling down the ramp, project F onto a unit vector V in the direction of as follows. So to solve this, here's our V here. So we're going to use cosine 30 degrees. 30 degrees, we're given that down here. Cosine 30 degrees I plus sine 30 degrees J. So we're 30 degrees J here, which would equal, here's our exact values for these two functions, b squared of 3 over 2i plus 1 over 2j. This would be our unit vector along the ramp here. Therefore, the projection of f onto v is, projection of f on the v would be f times v over the magnitude v squared v, and this would come out to f times v multiplied by v. Because v will cancel out one of these down here. So we plug in now. We have negative 200 multiplied by 1 over 2v, and then this will give us this exact value here of cosine 1/2, or rather, yeah, cosine 30 and sine 30, because of this 30-degree angle here from our ramp. So this is our degree, this is our slope here of our ramp. So we have negative 200 multiplied by 1/2 v, and then this would come out to negative 100 multiplying by these quantities. The magnitude of this force is 100, and therefore a force of 100 pounds is required to keep the cart from rolling down the ramp. So we can find the negative force here to stop the cart from rolling down the ramp. Let's do a problem now. A truck with a gross weight of 30,000 pounds is parked on a slope with d degrees here. Here's our ramp. Assume that the only force to overcome is the force of gravity. So A, find the force required to keep the truck from rolling down a hill in terms of slope d. So we have a d degrees of 30,000 pounds of the truck. So to set that up, we have F equals negative 30,000 J, gravitational force, and then V here would be cosine d degrees sine d degrees, and then our W1 would be projection of F onto V would equal F times V over the magnitude of V squared multiplied by V, which equals this becomes this over here. F times V multiplying by V would equal 30,000, negative 30,000, sine d degrees, cosine d degrees, sine d degrees. So negative 30,000 sine d degrees, cosine d degrees, and then negative 30,000 times sine squared d degrees is what this would become over here. And we multiply this through. We distribute this multiplication through the brackets here. And so when we put that into our graphing calculator, and then for d here we can find for the different percentages here of the slope of d. Okay, so we're going to use using your graphing calculator to complete this table here. These would be the different slopes of the ramp here, up to 10 degrees here. We go from 0 to 10. And then when we fill that out, we'll find that here are our forces here to hold that truck. Will be at 1 degree be 523.6. This got to be 547.0. This be 570 and etc. here. 209, up through 5 degrees here. That would be your solutions. And then as we get steeper here, we got to put more weight to hold the truck still till you get to 10 degrees on the ramp. You'd have to have a 5,200 pounds of force to hold it. And then find the force perpendicular to the hill. Find the force perpendicular to the hill when d equals 5 degrees. So W2 would be F minus W1, and then we have negative 30,000 J plus 2614. So our 5 degree amount would be 2614 here at 5 degrees. And then we multiply that through by cosine 5 degrees I plus sine 5 degrees J. And then when we crank this out, we get 2604.75 I minus 29,772.11 J. So this is what happens when we multiply through on these here, these values here. And so when we subtract this, see 2604.75 I minus 29,772.11 J, we get 29,885.8 pounds is what we amount to here. So that's what we would get. Okay, work. The work W done by a constant force F acting along the line of motion of an object is given by W equals magnitude of force times distance here. So magnitude of force times distance will be symbolized by PQ here within a double absolute value bars as shown like that. Force acts along the line of motion. Here is our line of motion here. And then this would be a diagram that would diagram this W. If the constant force F is not directed along the line of motion, if it's not directed along the line of motion, then the work W done by the force is given by W equals the projection of F on the PQ. So here's PQ, then here is F, projection of F on the PQ. This would be F here, and then here's our theta here, our angle of force in relation to our line of motion. Then the work W done by the force is given by W equals the projection of F on the PQ multiplied by the magnitude of PQ. So we need to know the force that's going along PQ. Projection form for the work. So we can use a cosine function here. Cosine here of theta times the magnitude of force times the magnitude of the line of motion. And this can be shorthanded like this. The projection of F on the PQ equals cosine theta multiplied by the magnitude of the force. So equals F times the line of motion P of Q, dot product form for work. This notion of work is summarized in the following definition. So the definition of work, the work W done by a constant force F as its point of application moves along the vector PQ is given by either of the following. 1, we have the projection of F on the PQ multiplied by the line of motion here of PQ, projection form, and then we have our dot product form. W would equal F times the line of motion PQ. So we have a dot product form of the definition of work, and then we have the projection form of the definition of work. So finding work. To close a barn sliding door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees. So here's our rope, here's our angle of 60 degrees, and this This pulls our barn door here shut. Okay, so find the work done in moving the door 12 feet to its closed position. Using the projection, you can calculate the work as follows. So our work here would be projection of F onto PQ. Here's our PQ. Then F would be the force multiplied by the line of motion here, PQ. Then we can use a cosine function for that because we're moving along the horizontal here. Cosine 60 degrees multiplied by force here multiplied by the magnitude of the line of motion PQ. So when we plug in our values here, cosine of 60 would be 1/2 times 50. We got 50 pounds up here for our force. And then our length here is 12. So we have 1/2 50 times 12. And we're going to find the work done in moving. We come up with a number here of 300 foot-pounds. That would be one way of putting it. So the work done is 300 foot-pounds. You can verify this result by finding the vectors of F and the line of motion PQ, vector PQ, and calculating their dot product. That would be the way that you could check this calculation here. Another way of checking that calculation. Let's try a problem like that. One of the events in the local strongman contest is to drag a cement block here. We got a 30-degree angle here. One competitor drags a block with a constant force of 250 pounds at a constant angle of 30 degrees with a horizontal. So here's our horizontal. Here's our 30 degrees. Find the work done in terms of distance d. So to find the amount of work there, we have F equals 250 pounds. I'm cosine 30 sine 30. And then our vector here would be PQ equals D times 1, 0. So W work would be F times vector PQ. So we have force 250 times PQ cosine 30 degrees be square root 3 over 2 times D. Be 1, 0. And then this comes out to 125 multiplied by square root 3 of d. So when you plug that into your calculator, you should get our work here, and we get 25. So our distance here for 25, this would be an amount of work here, 5412.66. Then for 50 feet would be this much, and then 100 feet would be this much foot-pounds of torque would be required for that. And that is your 6.4 part 2 pre-calculus math. This is my email for solution PowerPoints, for homework, notebook taking guides, anything else for the course. Thank you very much.